violent. Now, let's define what computational medicine isn't. Unfortunately, people get funny ideas when we talk about using artificial intelligence with medicine. And one of the reasons that this is a funny idea is because this is an example of what's called a non-deterministic system. We're going to talk about what that means. So a non-deterministic algorithm is one that's, it doesn't give the same output when given the same input. Now, why would scientists use something like this? Well, the reason is sometimes they see it as the only possible way to approach problems of a certain class. We're going to talk about these they're really two different types of problems. Now, a deterministic system is very different because it's much more predictable. It gives you the same output for the same input. So it's much more like a calculator. Now, the difficulty with design is basically it's much harder to develop deterministic algorithms to solve NP problems, and that's in the next slide. So a P problem, or a problem that runs in polynomial time, these are the simple problems. These are problems where you can solve them in a known exact number of steps. So most math equations, for example, you can easily use a computer to solve. But the big problems are NP. These are the non-deterministic polynomial time problems. They're problems that are so huge that we can't even figure out how to determine how many steps would be required. At least that's historically been the problem. So for example, a problem called the traveling salesman problem. This is where you're trying to find an optimal route to visit 300, in this case, 300 locations. The number of possible arrangements of those 300 locations is greater than the number of known atoms in the universe. So 10 to the 614th, it's huge. So how would you find the optimal combination or arrangement in that, that gigantic size? Well, so NP problems are very important in medicine. So for example, in various aspects of drug development and bioprocess design and optimization, synthetic biology. So how do you determine if a problem is NP? Well, generally, if you have to solve for a particular combination or arrangement or order, or the problem involves some aspect of guessing and checking if that's the best that people can come up with, like, for example, constraint-based scheduling, or in medical diagnosis. In this case, the computer's telling the doctors to flip a coin. And unfortunately, using non-deterministic algorithms tends to amount to something kind of like this, although maybe with a certain confidence interval. They say, well, you flip a coin, it'll probably be right. So we've identified a better way. And this better way is deterministic. So we built an AI engine that's based on the concept of leveraging constraints to solve these types of problems. So the idea is that once you can restrict the domain of the problem and identify exactly what the problem solution can't possibly be, you can eliminate all the things that aren't valid solutions simply by eliminating them at the source before you end up generating some ridiculous result set. So by eliminating the things that don't make sense, we're left with only the solutions, which allows us to approach these types of NP problems with the first deterministic system that's ever been developed that's capable of solving these problems. So there are a couple examples. We'll walk through a piece of one of them, which is a scheduling type of problem. So scheduling is a good example because it's fairly intuitive use of constraints. Let's say you have 400 employees, and each employee has their own schedule constraints, when they can and can't come into work. Well, we can use those constraints to build a model that could be used to generate perfect schedules that satisfy everyone's constraints. And so the way we do that is we build the constraint model. We have 3 orders of logic. The first, well, so after you identify the dimensions, in this case, various scheduling parameters, you build these constraints. First order constraints involve filters that allow you to identify various aspects. So like you could specify a particular employee and let's say a rule for where they'll work, such as location. And so from second order constraints, you can then build these third order constraints, which allow you to specify things like rules like that these 2 particular employees will never be able to work together. Let's say there's a work conflict. They got in an argument or something or fight. So they can never work together at the same location, same shift, any day of the week, period. And you can enforce a schedule, or a model that will generate perfect schedules that will ensure that those 2 employees never work together. So this applies to medicine in various aspects. There's a lot of research that's been done on constraint-based modeling. So we invite feedback, comments, questions. We are working on building a first production version of the application over the next 6 months. So we're looking for early adopters for alpha and beta testing. So feel free to reach out.